So this video is on section 1.4, working with radicals. Before we do that though, just going to give a little review on partial factoring. So here we're asked to find the vertex by partial factoring, and then state if the function has a maximum or minimum value and what that value is. And once we get the vertex, it's really to state what that minimum value is. And then just look at the a value, determine if it's a maximum or minimum. So the a value of the quadratic equation. So in order to partial factor, again, we create another function. I call it p of x, it's short for partial. And again, we only take the x squared term and the x term because we know that these two functions are going to have the same x coordinate of the vertex. So that's what we sort of discovered last unit. And so factoring an equation like this is going to be really easy because we can always factor out an x. In this case, we also factor out -3. So that leaves us an x minus 6. And we want to find the zeros of that. So in this case, that means x minus 3 is equal to 0 or x minus 6 is equal to 0. So what we discovered partial factoring is one of the zeros is always going to be 0. And the other 0 in this case is going to be 6. So this doesn't give us the coordinate of the vertex, but what it does is that with those zeros, we could get the x coordinate of the vertex by adding our two roots and dividing by 0. Think of it as the midpoint of the zeros or the average of the zeros. So in this case, it's going to be 6 over 2, which is 3. In order to get the y coordinate of the vertex, we need to go back to our original function, in this case f, and we just plug in the x value that we found. So in this case, the x coordinate of the vertex, which is f of 3. So plugging in 3 to our equation, we get minus 3 times 3 squared plus 18 times 3 minus 1. Well, minus 3 times 3 squared, which is 9. So minus 3 times 9 is a minus 27. 18 times 3 is 54 minus 1. So minus 27 plus 54 is 27. Minus 1 is 26. So therefore, vertex is at 6, 26. And because this equation has a negative a value, -3, that means it's opening downwards. So therefore, it's going to have a maximum. It has a max value. Again, maximum minimum value is always going to be the y coordinate of the vertex. So in this case, 26. All right, so let's go through a second example. We have g of x is equal to 2x squared minus 14x plus 7. Again, we define another function, p of x is equal to 2x squared minus 14x. Again, we want to find the zeros, and here we could factor out a 2x. So we get x minus 7. So in this case, we got 2x is equal to 0, or x minus 7 is equal to 0. So one of our zeros, again, is going to be 0, because we can always factor on x. That's the nice thing about partial factoring, and only dealing with the x squared term and the x term, is we'll always factor on x, and here we're going to get x is equal to 7. So the x coordinate of my vertex is going to be 0 plus 7 over 2, which is going to be 7 over 2. Well, the y coordinate of the vertex is we have to go back to our original function, in this case g of x. So plug in the x coordinate of the vertex, which is going to be 7 over 2. So here's going to be a little bit work since we have to deal with fractions. So we get 7 over 2 squared minus 14 over 7 over 2 plus 7. So here 7 over 2 squared is 49 over 4 minus 14 times 7 over 2, so that reduces to a 7, so it's going to be minus 49 plus 7. And here the 2's reduce with the 4, so we get 49 over 2. So here we're going to have a common denominator of 2, so I'm going to change these right away. So it's going to be 98 over 2 plus 14 over 2. So carry on this work up here. 49 minus 48 is going to be negative 49 plus 14. So negative 49 plus 14, that's going to give me negative 35. So this is going to be minus 35 over 2. So therefore the vertex is at 7 over 2 comma negative 35 over 2. And because this parabola or this quadratic equation has a positive a value, that means it's opening up. So that means that there must be a minimum value of negative 35 over 2. All right, so let's go a quick review of partial factoring. So here we're going to talk about radicals. So believe it or not, we've actually dealt with radicals already. We never called it that. And once you see what it is, you say, yeah, we've done it. But now we're going to go expand that notion of a radical a little bit more and some of the different operations we could do with it. So their success criteria is we would be able to express an entire radical as a mixed radical. So be able to convert an entire radical to a mixed radical and vice versa. So go back from a mixed radical to entire radical if need be. We're going to be able to add, subtract, multiply, and divide radicals. Radicals we're going to see is a lot like polynomials in terms, where we can add, subtract, multiply, and divide terms. It's going to be likewise with radicals. Then given expression, we could expand and simplify radicals. And we're not going to have to worry about rationalizing a denominator because that's for the enriched section only. So let's go off for some definitions. So what is a radical? Radical is the best way I would do it is just through an example. And like I said, we've worked with radicals before. So here we're going to have the square root of, let's say, 39. This in itself is a radical. So this square root is a specific type of radical. So in general, we have a radical. So another example we might have is, this looks like a square root. So again, we might have another number in here, 63. But in this case, we're going to have a little number inside that little nook of what would used to be called a square root sign. But we're going to discover that this is really the radical sign. So in general, it's the radical sign. The number inside the radical sign is called a radicand. And finally, if the number exists inside that little nook, it's called the radix. Okay, so the examples I've given up here, just as another example, the number in here inside the nook could be any number. So in this case, it could be a 10. And here I'm going to have 103 inside of my radical as my radicand. So all the examples I've given up here are entire radicals. Okay, in other words, really when we see a mixed radical, we're going to say that there's no coefficient being multiplied to a radical itself. So all the examples I gave up top are entire radicals. So it might be a big example of a mixed radical. Well, basically we take each of our radicals I gave you above and we multiply by number. So here 3 root 39. That's a mixed radical. I could do negative 6. And what we say the cube root of 63. That's also a mixed radical. And we could also have fractions if we want. So all those are examples of mixed radical. Like radicals are radicals that have the same radicand and radix. Okay, even if the radix doesn't exist. So just a little foreshadowing into Unit 2. When we don't have a radix here, it's actually implied to be a 2. Okay, we don't write the 2. Again, mathematicians are lazy. We figure they don't write a lot of zeros. They don't write a lot of ones. When it comes down to radicals and the radix itself, they don't write the 2. And there's a reason for that. Square root happens a lot. And so therefore, they're going to be lazy and say that, well, if the radix isn't there, we're going to assume it to be 2. Okay, so don't make the mistake that it's going to be 1. It's always going to be 2. So here, the radix could be 2 or non-existent, and that would be a like radical itself. So what would be some examples? Well, here 2 root 3 and negative 5 root 3. That would be an example of a like radical because the radicand is the same, in this case 3. In this case, the radix is the same. In this case, it's not written or it's an implied 2. Another example might be 6, the fourth root of 23, and negative 3, the fourth root of 23. So again, these two are like radicals because the radix is the same and the radicand is the same. An example of something that's not like would be something like 6 root 2 and 3 and the cube root of 2. So even though the radicand is the same, the radix itself here is different. That's a 3, and there's applied 2 over there. This is not a like radical. Okay, and we can't do anything with them in terms of multiplication, division, adding or subtracting. So when it comes out to simplifying radicals to a mixed radical, the concept is rather simple if we could kind of understand its purpose. So we just want to be able to see something in some of root 20 to see what value would that be without actually having to calculate. That's the idea of simplifying it. And so how do we go off and simplify it? Well, we want to break off 20 into factors, into two factors. And if we can, one of them has to be a perfect square. So in here, I'll just go down to a note. Factor the radicand into factors where at least one of the factor is a perfect square. So our perfect squares are here 4, 9, 16, 25, 36, 49, 64, 81, etc. Okay. Well, you could go off and memorize the square roots, or they're really easy to sort of determine. My memory sucks, but I can count to 10 really easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And really how to get the perfect squares is just score each of those. Because in essence, a perfect square is the number that you can square root and you get an integer. Well, in this case, we're just doing the opposite, squaring our integers, and we're going to get those perfect squares. Let me just clean up that 10. Looks a little bit sloppy. There we go. So here, this could factor into, while it could factor into 2 and 10, this doesn't help us because neither 2 or 10 is a perfect square. 20 also factors into 4 and 5. So that's the one combination we're looking for because in this case, 4 is a perfect square. So the reason why we do this is that we could break up that 20 into 4 times 5. And then one of the properties we have of radicals is that we could break that up into root 4 times root 5. We'll discover why we could actually do that, what the property in the next unit when we explore exponent laws. But in this case, take my word for it, we could split that up. And this is why we look for something that's a perfect square, because the square root of 4 in this case is 2. And then we're going to multiply by root 5, so we don't have to write an operation in between there, it's implied. And that's what all simplifying a radical really is. So finding a factor of a radicand that is hopefully a perfect square, and therefore we could simplify it. So in this case, when we have a square root of 147, well, this actually breaks down to 49 times 3. So this is root 49 times root 3, which is 7 root 3. This next example is a little bit tricky, only because we just need to be careful of something towards the end. So I'm going to do a longer version of this, but in the end, if you do a shorter version, we both get the same answers. So when we go through and sort of determine the prime factors of 48, we may only see, well, that's 4 times 12. 4 is a factor of 48. 4 is a perfect square. So this comes up to 2 root 4 times root 12, which is 2 times 2 root 12, which is 4 root 12. The thing that we need to be careful about is sort of like factoring, is when we get to the end, we got to see, well, is root 12, can that be simplified even further? Well, in this case, it can. So here, it's going to be really 4, and it can be broken down to 4 root root 4 times root 3. So notice here that I'm starting to shortcut steps a little bit. If we understand the process, we don't have to factor the radicand and keep it under the radical sign. We can sort of skip to the next step and say this is 4 times root 4 times root 3, which is 4 times 2 times root 3, which is 8 root 3. Okay, now can we simplify root 3 any further? We can't, and that's the final answer. If we could see that 48, well, the factors of 48 could be 16 and 3. So we saw that right away. While the square root of 14 is 4, and 4 times 2 is 8, that would have left us a final answer of 8 root 3 as well. So a little bit shorter steps, only if we could see that 16 was a factor as well. And the reason why this works is because 4 is a factor of 16 as well. So that's why it comes out that we can actually factor out 4 twice, and that's why we had to do this twice. So not the end of the world, just a little bit more work, but we're starting to recognize some numbers, some attributes. Maybe we want to try 16 as a factor first before 4, and that might save us a little bit of time. So here again were the instructions to do that. So after we factor the radicand into 2 factors, then we take the square root, the perfect square, and sort of it looks like it's being moved out of the square root symbol. Really, we're taking a square root of a perfect square. So in general, we have these properties of radicals where we have a root b times n root n. The net result of that, or the product, is the coefficients multiplied together, in this case a times m, and then under the radical sign, it's the radicands multiplied together, in this case b times n. Okay. Another property that we have of radicals is that we have the square root of a over b. This is also the same as root a over root b. And in this case, you can move either way. Sometimes we may have root 8 over root b. We may say convert that to a single fraction and take the square root of that entire thing. Of course, the most important thing to note here, or one of the important things to note here, is that b can't be 0 because we can't have a denominator 0. So this is really going off into an example where we're sort of undoing what we did. I'll be honest, it's unlikely we ever ask you to do this. Most of the time we want you to simplify a radical, but in this case we want you to go in the opposite direction. So in order to sort of put 2 under the square root sign, we sort of have to do the opposite. Now we need to square it first and then multiply by 10. So this is really square root of 4 times 10, which is square root of 40. Likewise for the second question, I'm going to shortcut this a little bit. So this is the same thing as square root of 9 times 5, because 3 squared is 9. So this is root 45. This next question is a little bit tricky because we have a negative 3 root 8. So really what we want to do is, because a final value or value here is negative, we want to keep the negative on the outside, because what happens if we move the negative, or we take the negative 3 squared, that becomes positive, and now all of a sudden our entire radical is positive, which doesn't make sense because their value originally started out to be negative. So what we want to do is we want to keep the negative outside. So this is really 9 times 8 as a radicand. So it's going to be negative root 72. So here are some examples where we'll make use of that division property. So root 8 over root 2. This is going to be the same thing as root 8 over 2, which is same thing as root over 4, which is just 2 now. This next question we could do likewise. So in this case, this is the same thing as 2 times the square root of 24 over 3, which is 2 times root 8. And if we simplify root 8, that's going to be 2 times root 4 times root 2, which is 2 times 2 root 2, which is 4 root 2. Determine the following is true or false. So one of the things that I've preached since grade 9 is adding and subtracting screws us up. So this property of root a plus root b does not equal to root a plus b, right? So we discovered up above, root a times root b does equal to root a times b, but what is adding in there, that doesn't apply. So a lot of things that we did with exponent laws in grade 10 and grade 9, adding and subtracting screws us up. So there's very little that we could actually do to simplify that. One example to kind of prove that this is not true is just saying a to 1 and b to 1. So in this case, it's going to be 1 plus 1, which is 2, which is not equal to root 2. And I would argue that you could almost choose any values for a and b, and it will not work out. So we want to add and subtract radicals. It's a lot like polynomials, where we're adding and subtracting is adding. We can only add and subtract like radicals. So adding and subtracting radicals is like adding and subtracting polynomial terms, where we can only do that if they're like radicals. That is, radicals with the same radicand, and I should also put in there and same radix, because that was the definition. But for this unit, we'll be usually working primarily with square roots. So in this case, 3 root 5 plus 8 root 5, it is a like radical, so we just add the coefficients, just like it was polynomials, and this is going to be 11 root 5. For example, number B, again, we do have like radicals in there, root 10, so negative 7 minus 4 is a negative 11 root 10. And the last example, it looks like we can't add them because the radicands are different. So it does not look like they're not like radicals. Well, remember we have to try to simplify things. So 6 root 3, we can't simplify that anymore. But we discovered, as we did up top, for example, root 48, that we can simplify root 48. Well, 48 breaks down to 16 times 3. So it's going to be root 16 times root 3. So this is 6 root 3 plus 4 root 3, and look at that, lo and behold, they are like radicals now, so we can add the coefficients, and the final answer is going to be 10 root 3. Okay, so it seems like it was tricky, that we couldn't. Just remember that we always want to express the radicals in the simplest forms, and then once we do that, there might be opportunity to combine like radicals. The last example we're going to go through here is multiplying or distributing radicals. So this is a lot like, again, polynomials. We'll take a binomial times a binomial, and we do FOIL, or what I used to call the rainbow method, where we distribute across. So the first one is going to be root 3 times root 6. I'm going to write these out explicitly as I'm going through. So I have a root 3 times a root 5. And then I have a negative 5 times a root 6. So negative root 5 times root 6. And then finally negative root 5 times root 5. Okay, so just writing it out, just being systematic in my FOIL. So I just kind of see what needs to be done. So here you can see this is going to be root 18. So I just multiply the radicands together now. Plus root 15 minus root 30. And then minus root 25. Okay, now some of you might have saw that root 5 times root 5 is going to be just 5, but I just, being common across, simplifying each of my terms there, just multiplying the radicands. So root 18, this breaks down to really root 9 times root 2, so I can simplify that. Root 15, I can't do anything with. Root 30, I can't do anything with. And as we said above, root 25 is just 5. So one last thing we do is just take the square root of 9. So this is 3 root 2 plus root 15 minus root 30 minus 5. Everything is simplified, and unfortunately we cannot combine any more radicals together. So that really is our final answer. As unsimple as that looks, that's as simplified as we can get. Last example is really kind of similar, so we have some coefficients in there, so we have some mixed radicals. So here again, we do my FOIL. So here I'm going to 5 times 3 is 15, and I'm going to do everything kind of at once now. 2 times 8 is going to be root 16, and then the next one is going to be negative 5 root 14, and then this one over here, that's going to be 3 plus 3 root 48, and the last one is going to be a minus root 42. So luckily, or this one works nice, root 16 is actually 4. I can't do anything with root 14, so that's going to stay. So 5 root 14. Again, another example of root 48. So third times the charm, recognize that this is going to be root 16 times root 3. And then root 42 is not divisible by 4. Therefore, it's not divisible by 16, not divisible by 9, not divisible by 25. Looks like there's nothing we could do root 42. So here we get 15 times 4, which is 60, minus 5 root 14. 3 times 4, because root 16 is 4, that's going to be 12 root 3 plus root 4. So not plus or minus root 42. And that's the final answer. Can't simplify that any further. Yes, that root 42 looks troubling to me. You think, oh, maybe we could get it as a root 3 somehow and sort of combine that 12 root 3 with it. Don't force things. That's the end. We can't do anything root 42, and that's the final answer. So just for those who are interested in rationalizing the denominator, what that means. In proper form, we never want a radical in our denominator. So ideally what we want to do is express our final answer, simplified answer, with no radicals in our denominator. So in this two examples, we have 5 root 6 minus 1 over 2 root 2. So here we'll talk about rationalize the denominator. Really what we want to do is just multiply our fraction in this case by 1, but a special way to express 1. So we could rationalize, or we could turn any radical into a whole number just simply by multiplying by itself. Because in this case, root 2 times root 2 is going to be 2. So really that's the secret behind this. Really take an expression, multiply by 1, but in a very special way. So in this case, we're going to have 5 root 12 minus root 2 over, in this case, I'll write it out explicitly, 2 root 2 root 2. And the whole idea behind that is in the bottom, when you get 2 times 2, well, at the top, we have an opportunity to to simplify root 2. So that's going to be 5 times root 4 times root 3 minus root 2. And so here, my final answer is going to be root 4 is 2 times 5 is 10, root 3 minus root 2 over 4. Okay, so here we just rationalize the denominator in that way. The next one is a little bit tricky because we have two radicals added subtracted together. So one of the things we're going to learn is a trick about the conjugate. So conjugate is if, for example, we have A plus B, the conjugate to A plus B is really A minus B. And one of the things that we kind of remember maybe from grade 10 is when we sort of expand that is what we get a difference of squares. So in this case, it's going to be A squared minus B squared. So notice that the A's and B's sort of disappear and we have A squared minus B squared. So that's a trick with the radicand, sort of with this one to rationalize the denominator, is we want to multiply by the conjugate of root 5 minus root 3. So the conjugate of root 5 minus root 3 is root 5 plus root 3. So again, we really multiply it by 1, but in this case, a very convoluted way, but a convoluted way with a purpose. So this is why we did the examples up top where we're sort of foiling things. So 1 times root 5 is root 5. 1 times root 3 is root 3. Negative 2 root 3 times root 5 is going to be negative 2 root 15. And negative 2 root 3 plus root 3 is going to be negative 2 times 3, because root 3 times root 3 is a 3. Now in the denominator, we're going to get root 5 squared, which is just 5, minus root 3 squared, which is 3. Again, we got this from the A squared minus B squared attribute. So here we're going to simplify the top. I'm going to get root 5 plus root 3. Can't do anything with the 15. So negative 2 root 15. And finally, the last term there is going to be minus 6 all over 2. So in this case, this is how we rationalize the denominator with something worth two radicals added subtracted as a part of the denominator.